It's another storage video, and I mean, you know, what sort of crazy person is gonna have, you know, just all this storage? It's just completely insane. Are those P5800X Optane?
Yep.
So I'm joined by a very special guest, Allyn Malventano. You know your stuff. It's exciting.
Sometimes.
We've got a lot more Optane stuff. And basically the story is I wanted to run a whole bunch of experiments. I've only got the two vastly superior, let's say, Optane drives.
He needed a few more.
Yeah, we needed to run some more tests. We wanted to put some, fabric pressure testing in order to like figure out how many threads does it take to load up a single drive in a worst case scenario, and what is the absolute maximum number of IOPS that we can see on any platform. And we had the highest end platforms to test, both Epic 7763, Threadripper Workstation 3975WX. I think it's the 32 core.
Oh.
Well, we did 32 and 64 core testing.
Yep.
So the 3995 as well. And Xeon Platinum 8380s. 80 cores of madness. And hitting 10 million IOPS takes about 5 drives. That's insane.
Isn't that ridiculous?
Yeah. Now, admittedly, that is a best case scenario. Intel's rating for these drives is what, like 1.5 million IOPS?
Yeah, it's around there.
So, but you can, if you create some artificial workload scenarios, you can actually achieve more than 1.5 million IOPS, which is really pretty impressive. I mean, you contrast this to NAND flash, and we've done reviews of other NAND flash devices, and out of the box, it's like 1.5 million IOPS, and then you put more than 20% of the capacity on there, and then it's like 600,000 IOPS.
Yeah, these don't care.
Yeah, they don't. They really don't.
They don't care, especially if you do full span I/O, like all day long.
We filled
just
them
doesn't change.
all the way up, and it doesn't matter. It doesn't care.
Yep.
It is really exciting. I see every time I'm gushing about Optane, I see a lot of people ask questions about things like, well, if you have efficient caching, doesn't that make a lot of the need for Optane go away? And yes and no. So for like just raw, like I'm going to recompile open embedded, yeah, you can make a lot of that go away with RAM caching and just throw more RAM at the problem, that kind of thing. The problem is that not all the software engineering has been done in all the scenarios where there is actually a caching mechanism there.
Yep.
One of the other things is Intel SPDK. So like I've been messing around with SPDK a little bit, and spoiler alert, the hard limit in the Linux kernel is around 10 million IOPS, at least on modern hardware.
Yeah.
Because the context switching, and the spin locks, the I/O, and the interrupt handling or poll queues.
Yeah, you can't throw more hardware at it and make that go away.
Yeah, no. And so what Intel did was they ripped out all of that and replaced it with something called SPDK, and
Gets rid of a lot of the layers.
yeah, it gives you more of a direct. It's more like interfacing with memory, really, because there's less overhead, there's less you have to think about, and it really is a computer science problem. It's a really interesting computer science problem.
When storage is fast enough to where everything else becomes a bottleneck.
Yeah, the databases are probably the easiest way that you could explain it. So like for you non-computer scientists in the audience, when you're working on a database is a huge, complicated spider web black box of insanity. And all modern databases implement something called a transaction log. And if something unpredictable happens, there's a software bug, a power outage, something, you can shatter the entire structure of the database to where that it doesn't make sense anymore.
Yep.
A transaction log is a ledger of all of the stuff that has been done to that database since the last backup. You can take last night's backup plus the transaction log and get to where you're supposed to be, or troubleshoot the bug, because databases are that critical. And if you really dot your I's and cross your T's, because Optane is so low latency, and because of some of the mechanisms that it offers from a hardware perspective, this is more to do with DIMMs than NVMe, but you can do this on NVMe for a more ghetto fabulous version. You can store the transaction logs on Optane,
Yeah.
and a lot of the architectural shenanigans that happen in a database go away. And so you end up with much better database scaling because you're able to make certain architectural changes and architectural differences. And these same kinds of things on NAND is really hard to do. When you look at competing NAND technologies, things like the Samsung 983, they have to implement it with power loss capacitors and onboard DRAM.
Yep.
And that introduces, it's like, well, it's okay in most scenarios, but it's not okay in every scenario. This, you don't have to think about that. It's just going to do it.
Yeah, for NAND, usually your write latencies, as long as there's not a bunch of load on the device, your write latencies will usually look pretty darn quick. Like they'll almost look like, you would think, oh, it's almost like it's going to RAM or something. Like it's super low latency. Technically, it is, right? Yeah. It's going through the controller and to the input, RAM buffers on, like basically SDRAM.
Yeah.
On the dies of the flash. Yeah. Right, so it hasn't actually moved from that into the flash yet in that moment.
But it's told the computer, that was written out. It's like, well, it wasn't really.
Right, and so for these, if you compare like a brand new modern Gen 4, NAND-based SSD, the QD1 like write latencies, they'll actually be a little lower than these.
Yeah, it's going to RAM.
Because it's going to RAM. But when the Optane drives respond to the host, it's already committed.
Yeah. It's like actually it's been written. Medium.
Yeah, it's done. You could lose power right then. Yeah. And it'll still be there when it comes back. Right.
And the level of engineering that, I mean, even the Intel, like the P4511 M.2s that I have huge, probably 10% of the board area on those 110 millimeter M.2s is power loss capacitors. And they have, this incredible engineering to be like a computer within a computer, so that when the main computer loses power, they've got enough backup power that they can dot the I's and cross the T's.
Yeah.
But that is a much more elaborate and complicated setup than just the medium is that fast.
Yep.
And that's also really exciting from the DIMM side of things, because the DIMM side of things ups the throughput even more. It's like, it's not as fast as traditional memory, but when the computer loses power and it gets power again later, it can just resume right where it left off.
Yeah, and the latency of the DIMMs it's insanity. Yeah. It's like 350 nanosecond latency to the DIMMs compared to, those are like 6-7 microseconds. So it's almost like another 10x on top of that. And it's, it's the same media. It's just all the other hops you have to make to go across PCI versus just direct to the CPU.
Yeah. In some ways, where we are with the software engineering is it requires less software engineering for a better result, because all of the layers that we've added to protect ourselves from the crazy go away if you have this additional storage layer.
Yeah.
But also, because of that, all of the traditional existing stuff needs more software engineering to take advantage of that, or more software engineering to take advantage of that as some type of like caching or middleware layer. Because if you just add it as caching, then you've also got the latency of like driver overhead to deal with that. Mm-hmm. Whereas you can just store it on this. You don't have driver overhead. You don't have anything to think about. You don't have a lookup table to figure out, okay, is this something I should put in cache, or should I write this to the device? That requires computational overhead.
So funny. It's like decades worth of engineering efforts spent on something that, like, imagine if that came to be like 20 years ago.
Yeah, it would be...
Computers would be completely different.
Yeah.
By now, right? Like,
people would just be like, you have to have this. And it's like, oh, okay.
Well, not only that, but everything would be kind of like designed around it, right? You would just, instant on would actually be a thing, right? Because it just, all your stuff is already there. You just turn it on. It just starts executing right off of it. Like that, those sorts of things could happen.
It would be a return to the way it was in the 60s, where like the big mainframes, they had the execute bit.
Yeah.
Oh, my PyDP 11, I can hit a button on the front of it and halt execution, change the state of the machine, and then flip a button and resume execution. Mm-hmm. That's how it was in the 70s. Mm-hmm. And it's like, oh, the machine lost power. It's like, well, the information would be retained in the bits for hours after power loss. So like if you only lost power for 10 or 15 minutes, you just turn the machine on and then you start executing again, and it's fine.
I am a bit jealous of that thing over there. I need to get me one of those.
Yeah, so we've had a lot of fun benchmarking Intel 8380s, mm-hmm. and got some surprising results, and we've got to do some homework there.
Yeah.
And then we've also tested 4 or 5 Optane in Threadripper workstations. Mm-hmm. And the thing that my main takeaway from this is that, there's really pretty severely diminishing returns much past 4 or 5 Optane devices, as long as you're not using something like SPDK on top of it.
Right.
Because between the spin locks and the software overhead and that kind of thing, you really lose a lot. Well, I've got some content planned to go over some of the things like GPU Direct, because I was doing some testing with GPU Direct, and the numbers there are just as bananas, because without the CPU doing anything, and it's just like, oh, the video card can read directly from storage, how fast you can load a texture changes dramatically. It is completely insane. So you add something like this, and it's like, well, it's not quite as fast as main memory, but it's not ephemeral like main memory. It's like, oh, I need to preload the game texture. No, you
it's
don't
just
have
there.
it's just, you just load it. It's good to go.
That is cool stuff coming. All that direct storage stuff and everything. Microsoft's working on that.
Yeah, just the little things, little inefficiencies will snowball into something that is just completely untenable. See also 10 million IOPS limit in the Linux kernel. Now you can go a little beyond that, like with tuning and really like you want to dive into it. I can squeeze 15 million IOPS out of a single socket, but
when you get to 2 socket, weird things start happening.
Yeah, and that's some of the stuff I think that we're seeing, but you're gonna have to stay tuned for that. I've got a write-up with some more benchmarks and some more FIO scripts on the forum that you can check out. I really like breaking systems to see like, okay, there's so much storage here that the BIOS has locked up.
Yeah. Yeah, or the whole system. There's that weird thing with MD that you and I have been trying to get to the bottom of, right? Like, only if you have fast enough storage in the system and enough load to throw at it does only some particular types of ways of making an array in Linux not just like crash the kernel or anything like that. No, just hard lock.
Yeah, it's not
like
even,
you just don't even you don't get any error message. You don't get nothing. It's just like
magic
done.
System request doesn't work. Nothing. And the thing that we reproduced earlier, the IPMI was working initially, and then the IPMI hung.
Yeah.
And so I think we accidentally overwrote like memory space that IPMI was using or something, because the IPMI was like, okay, here's a login form, and then you log in successfully, and then it was like,
yeah. And it was like gone. You couldn't even reconnect.
Yeah.
Like I've never seen an out of band management like that just become in band and scrambled and
you can send it commands. I mean, it's connected by the message bus.
Sure.
And a bunch of other things, but yeah, something weird is going on there. I don't get what was going on.
And then the other instance where I actually scrambled the BIOS or scrambled something in such a way where I couldn't even reboot the system. I had to reflash.
I did that too, but I can't reproduce it reliably. Yeah. I can get the system to lock, but at least one time it was like, oh, I can at least I can reprogram it. That's okay.
We're 5 layers deep on the obscure configuration, like bleeding edge CPUs and platforms and storage, and
it's a leaky abstraction. Really leaking. So it's pretty exciting stuff when you think it through and you do all that kind of stuff. So be sure to check out that forum thread, look for that, and look for more other future videos with SPDK. But if you also have any questions about super insane fast storage and enterprise storage, and it's like, hey, does this make sense for my workload? I don't know, but we can figure it out. Let us know. Maybe I can get him back and we'll be like, let's solve your problem.
He keeps pulling me back in.
Well, there's so much storage happening. What else do you expect?
That's true.